Okay, then, yeah, welcome to this last exercise. I would like to continue with what we did in the lecture. And I said it's a bit complicated setup here. My computer would not connect, so I'm running a parallel Zoom meeting to project something here on the screen. But hopefully it would somehow work. So if I share my screen, now the question that we are trying to solve is what is inside this filter, right? Remember that in the lecture we had this filter from Würth Elektronik, and using my analog discovery 2 impedance analyzer, we measured impedance from this side with this open and short-circuited, impedance from the other side with this port open and short-circuited. And yeah, so now we are trying to find out what is inside this filter. And so the things that we have measured was, as said, the input impedance for the open circuited case, input impedance for the short circuited case. And maybe let's try to draw a schematic for this, as I've done before on the whiteboard. So let's say this here is our filter. I will just draw it as a black box. And we have the input side. So this is the input. And this is the output. And what I've always measured was the impedance from a certain side. So this is what I've called input impedance. And the first measurement that was presented here on this slide was for the case that the output was open circuited. And what kind of behavior can we see here?
Capacitive.
It's capacitive, because the impedance, this is the magnitude of the impedance, this goes down with frequency, and the phase is at around minus 90 degrees. So we can guess that inside this filter, at this position, there should be some capacitor, or in German condensator, exactly. Okay, and so then the other measurement that I did was when the output was short-circuited, and if the output was short-circuited, the impedance behavior looked like this. So here can we see, as you mentioned, at least here some inductance, because impedance is increasing with frequency, and the phase goes to plus 90 degrees, but here at the beginning for small frequencies we see that the impedance stays constant and that the phase is also nearly at 0 degree, and then we see here some kind of resonance, and the impedance goes down and phase goes to minus 90 degrees. So we can guess, okay, if we short circuit this here, there must be some inductor here, so that we see this inductive behavior. And at really high frequencies, then it's more challenging for the current to go through this inductor. So it will be easier to go through the capacitor. So we see the impedance of a parallel circuit, a parallel connection of capacitor and inductor. And so this is also the impedance behavior of a parallel resonant circuit. And so we could also think about this resonant frequency here, for example. Okay, so and then the remaining measurements where I also measured the impedance from this side, and this is what I called Z out. And this was also for the case that this was open circuited. And as you can see, okay, if we measure this from this side with the open circuit, we see a series connection of L and C, and of course at low frequencies the C is dominating. So this was this measurement result. At low frequencies it's more like a capacitor, and then we see another resonance, and then the inductor kicks in. So this is the impedance behavior of a series LC resonance circuit. And once again, we could calculate the resonant frequency. It would be the very same formula, the very same value. Okay, And so the last measurement was if we had a short circuit here at the beginning measuring from the output, and then of course if we have the short circuit here, the capacitor is short circuited, so we should only see the behavior, the influence of the inductor, and this is also what happens here. So just the resistance of the wire that the inductor is made of, and then the inductive behavior, impedance increasing with frequency. Okay, so these were the 4 impedance measurements, and then in the lecture I also measured the transfer function. In the lecture the result did not came out that nice because I think maybe some of the probe cables was not the correct one, but here we can clearly see low pass behavior, low frequencies can get through. Here are the 100 kilohertz, then the filter starts to attenuate, and in the ideal world the attenuation would just continue to increase. Transfer function should go down, but here we see another resonance approximately at 500 kilohertz, and then the behavior gets worse. And so as said, the idea is to find out what is inside the filter. So we already, when looking at this, found out, okay, there must be some capacitor and there must be some inductor, but what values do we need for the capacitor and for the inductor to get a good fit between measurement and simulation? And for this I've prepared LTspice simulation files. So the first link is not really relevant if you already have LTspice, and the second link, there you can download the zip file, and once you open up the zip file it should look like this. That there are 4 folders, one for the transfer function and one for each of these impedance measurements. And if we open up the first one and open up this one here for comparison, then the upper part of the circuit is just there to replicate the behavior of the measurement. So what I did is from this measurement here in the analog discovery to waveform software, I exported this and I imported this here, changed the data format a little bit. So this block here replicates the impedance. We apply a voltage, we can measure current. From this we can calculate impedance. And now here we can draw our filter circuit. And as discussed before, we need to have some capacitor, some capacitance. So let's add some capacitor. And let's wire everything together. And I will just omit the inductor in this case, because if there's an open circuit at the output, there would be no current flowing through the inductor, so the inductor has no influence on the result here. And then of course we need to find out what value does the capacitor need to have. And so what have you found out? What is a good value for the capacitor? 100 nanofarad, right? And so I will select 100 nanofarad. Not 100 farad, 100 nanofarad. And then we can see, okay, that directly from scratch, maybe if I tile the windows in a different way, that we get a very good behavior for the magnitude already, not for the phase yet. And we can see, okay, if we increase this value, more capacitance should give less inductance, less impedance, I'm sorry. Yeah, so then green curve is the measured result, blue curve is the simulated result. So now we get less impedance. If we take a smaller value, if I would just take 50 nanofarad, then we get an impedance that is too high. So 100 nanofarad makes a good fit, makes a perfect fit. Would there be another way to find out about the correct value of the capacitance that we need to use?
You can take 2 points.
Yeah, we can take a point. So for example, if I use a cursor, let's move the cursor window somewhere up here. And if I move this cursor to be at a nice frequency of, let's say, 1 kilohertz, which is somewhere here. So at 100 kilohertz, we can see we get 1.62 something. It's very small on the screen, but 1.62 kilo ohms of frequency. So the impedance of a capacitor, what is the formula for this? Yeah, it's 1 over j omega and c. And so if we are just looking at the magnitude, okay, we can neglect the j. And omega, the angular frequency is, how can we calculate it from the usual frequency? 2pf. And so if we want to have the capacitor, we can rearrange the formula to 1 over 2pf and the magnitude of this impedance. And so if we insert these values for a frequency of 1 kilohertz, and Zz is, or the magnitude is the 1.62 kilo ohms. And now I might use Octave to calculate this. So there's an Octave window, or Octave should open up. So there we go with Octave. And F is 1 kilo, omega is 2 times P times F. Oops. Omega is 2 times P times F. And Zz was 1.62 also kilo, 10 to the power of 3. And so if we calculate C as 1 over omega and Zc, and convert this into nano, so multiply with 10 to the power of 9, we get almost 100 nanofarad. So the 100 nanofarad make a good fit. But we can see that the magnitude is fitting quite well, but the phase isn't. And why does the phase not really fit? Because the capacitor in real life is not a perfect capacitor. The capacitor will at least have some small series resistance for the wires that connect, or for the packaging that connects the capacitor. So we can add some equivalent series resistance. And we can take a lucky guess, for example, 1 ohm. And then we see, okay, we get some phase shift that now goes to 0 degree, which makes sense because 0 degree is the phase shift of a resistor. But the phase shift is a bit too large, so we select less. What value have you chosen to get a good fit?
I choose
0.75. For example, 0.75 with 0.75, we get a quite nice agreement for the high frequencies. Still not a good fit for the low frequencies. So we need to have another resistor. What is the other option that we have to place a resistor? In parallel. And of course, the parallel resistance here should be rather large, because if we would have a small resistor in parallel to the capacitor, this would always short circuit our filter, which would not make any sense. So it must be a rather large resistor. And so we can try, for example, 100 kilo ohm, and then we see, okay, this gives the wanted effect, but it's way too strong. So what do we need to do? Take even the bigger resistor. So bigger resistor makes less current going through this resistor, less effect of this resistor. So which value have you chosen? 1 mega ohm or 1000 kilo ohm. And with 1000 kilo ohm, we get an almost perfect fit there. So there is, maybe I will add this here. So there is some quite large resistor on purpose in parallel to the capacitor. Can you imagine why in this filter, why we have this is the input side, why there is a resistor on the input in parallel to the capacitor. What might be the useful purpose of having a resistor there in parallel to the capacitor? I mean, here there's some power cable. Yeah, so imagine you have some device, and this device uses this filter at the input. So you have your power cable. You have the device, and at the other side of the cable, there this filter would be connected. And so at the input of the filter, as we can see, there's this capacitor here. And so now imagine that you unplug the cable exactly in the moment where the mains grid voltage has its maximum. Of what is the maximum voltage that you have in the mains grid? Yeah, 230 volts is the RMS value, but the maximum value, the amplitude, is square root 2 times larger, is 325 volts. Yeah, so if the maximum here, the sinusoidal voltage, if it's maximum, and the maximum is, as said, 325 volts. If you exactly in this particular moment, if you pull out the cable from the power outlet, and then there's this filter connected, there's a capacitor that is charged to the full voltage. And so now if you would take the cable and touch it, or then you would get some electrical shock due to this voltage. So the purpose of the resistor in parallel to this capacitor is to discharge the capacitor over time. It's a pure discharging resistor. Okay, so this parallel resistance here is there on purpose. Okay, so we have a nice fit. So now I will close this, move this to this side here, and we'll open up the next schematic, which is the one for the input impedance with a short circuit at the output, and move it here to this side. And now I can delete this here and go to copy here. So I'm using the old interface. I think this here is, oops, no. This was not the wrong thing. Was not the right thing. So tile vertically. This here means copy. So we copy the capacitor. Wire everything back together, and I should have also copied the ground node. And now we need to have the next element, which is the inductor here. And so I select some inductor, rotate it with Control R, set it in, and wire it together. And now we need to have a value and a lucky guess for the inductor. So which value have you found out for the inductor? 50 micro Henry. So if I select 50 micro Henry, if I close this and click on simulate, and maybe once again tile the windows vertically, then it fits better on the screen. Then we can see, okay, with the 50 micro, of course, the values of the capacitor should not change because between measurements, it should be the same capacitor. So now we should only change values of this inductor to get a good fit. And with the 50 micro, what fits at least is this resonant frequency, which also somehow makes sense. And so we could also try to calculate this. Do you know the formula to have the resonant frequency of a parallel or series resonant circuit? Yeah, it looks like this. 1 divided by the square root of L and C. Have you seen this before? This formula?
In the resonance gap.
This is the resonant frequency. So, yeah, and now we could go back to here, put a marker on this, move the marker to the resonant frequency, which is somewhere here, right? And then we can see the resonant frequency is at around 69 kilohertz. So our resonant frequency, or yeah, we could also just say 70. So it's 70 kilohertz. Omega, once again, is 2 times P times F. We already know the value of C. So if we want to have L, then L should be this.
1 over.
Yeah, 1 over. So it's let's say better to have here a square and to remove the square root. And then we can see it's 1 over omega resonance squared in C. Right? This should be the right formula. So going back to Octave, we can say the resonant frequency is 70 kilohertz. So our omega resonance will be 2 times P times F this. And so then L will be 1 over omega resonance squared and divided by C. And then we get something else. Does this make sense? Okay, this here is wrong. This should be, of course, resonant frequency, and then we can calculate the L again. And then we get, yeah, so if I multiply L with 10 to the power of 6, we get 52. So maybe let's use this value, 52.6 or what, micro. Okay, and then we get a good fit for this resonant frequency. Still, the agreement here for the magnitude as well for the phase is not really good. And also the resonance is a bit too peaked. So, yeah, what do we need to do to get a better agreement, and why? So, of course, this inductor is also not a perfect inductor. If I take from this here Würth Elektronik Design Your Filter kit, if I take one inductor out of this box, like this one here, so then this is how such an inductor looks like, and it's made out of wire. The wire has a resistance. This is a series resistance for the inductor. And then the red stuff is the core. It's some ferrite material, so it's kind of a metallic magnetic powder, because you want to have permeability, but you don't want to have too much of conductivity, because this would create eddy currents. But still at the end you want to have some losses inside there, because it should act as a filter and somehow dissipate the unwanted energy. And so due to the wire we have series resistance, and due to the core we have parallel resistance. So if I add a series resistance, which value have you chosen? And why? 1.5. So we can check if I say 1.5, then what should happen is, of course, that the series resistance should be measurable at the low frequencies. So here now it should change. So if I resimulate, okay, then it changes there. It was almost a bit too much, maybe, because the measured the measured value is, if I would add the cursor once again, is something like, I think, 1.2 or so. So yeah, here we can see we get 1.2. So with the 1.2 we get an even better fit, maybe. Okay, and then it's still a bit too peaked here. So we need to have parallel resistance and a reasonable value. What have you chosen? I think something like 200 might fit quite well. Yeah, so with 200 we get a very good fit. So a very good fit here and a very good fit there. Not a perfect fit in between, not a perfect fit for the phase. Why is this? Because once again, it happens a bit more than just RL and C in there, because the copper wire, there will be something like skin effect. Have you heard about skin effect? So there are also eddy currents in the wire, and at higher frequencies the current will be pushed to the outside, will only flow on the skin of the wire. And this increases frequency, but it increases the frequency proportionate to the square, or it increases the resistance proportionate to the square root of frequency. And this effect is not included in our model. And also the losses, the permeability, the conductivity of the core material, they will also change with frequency, and this is not included in our model. And that's why, okay, as Edward Pelham-Box said, all models are wrong, but some models are useful. Yeah? And we cannot get a perfect fit. Okay, so let's close this once again, move it over here, go for the next model, open up the one with the output impedance in the open circuit case, move it over here, and now it should be fairly simple to just copy the filter. So I will go to copy all stuff, move it over here, take the wire tool, wire everything together, and because the filter elements should not change, we're just changing the measurement. If I close this, start the simulation, rearrange the windows in a better way, so then we can see, okay, directly from scratch we get a very good fit, because all the circuits elements are now already correct. And so once again I will move it over, open up the last model, which is this one here, make it fit to the window. Once again, remove this one here, take the copy tool, which is this one here, copy all stuff, move it over here to this place, wire everything together, and then the only difference now is that it's due to the short circuit at the beginning, the capacitor has no influence anymore. And if I close this, click on simulate and tile vertically, then you can see that we also get a quite nice fit here. So it works for the low frequencies due to the resistor, it works at the high frequencies due to the inductor. And in between the fit is not that nice, because in between we also have the range where the skin effect and so on gets effective. Okay, but at the end it's not too bad. So let's also close this. Once again, move this over, open up the last model, which is the one for the transfer function. And I will once again move this over to this side, take the copy tool, copy all stuff from our filter, paste it in here, remove the comment, take the wire tool, wire everything together, and close this, click on simulate, rearrange the windows, and then unfortunately I was not really able to import, or I had not enough time. It's probably also possible to import the measured values here, but here we have to do the comparison maybe like this, that I tile the windows horizontally and then move over to the slides, maybe do it like this, and then where is Seiten fortlaufend anzeigen? Okay, so this was all the impedances and this was the transfer function. So here's our measured transfer function and here's the simulated transfer function. and then you can see the fit is not that. If I try to move it to the same frequency range, so here we are starting from 100 Hertz to 10 megahertz. We can see for the low frequencies is 5 minutes. Yeah, so here it's fitting. For the high frequencies, it's not fitting. And one question is, for example, why do we directly start with the 6 dB or minus 6 dB? Who's good in 6 dB, in dB calculation? What does 6 dB mean on a linear scale? If you convert 6 dB into linear, if a voltage is 6 dB higher than another voltage, by which factor is it higher? Say again? 2 times. So this means this is a factor of 2. And minus 6 dB means it's like multiplied by 1 over 2. So where does the 1 over 2 at low frequencies come from? The minus 6 dB that we see here and the minus 6 dB that we see here. It's because we are measuring this impedance with some resistance at the input and some resistance at the output. And so if we, at low frequencies, this will be a pure short circuit, this will be a pure open circuit, so we just have this voltage divider of 2 equal resistors, and 2 equal resistors will give a factor of 1 over 2. This is where the 6 dB comes from. Okay, but still, unfortunately, yeah, there is something more that happens in the measurement that we don't have in the simulation, because in the simulation it's perfectly going down and we don't have this resonance where the filter behavior gets worse once again. So there's a last effect, there's some last thing that we don't include in our model or that we neglect in our model. Some last parasitic unwanted effect that unfortunately happens there in real life that is not yet included in our model. And what could be the reason why the filter in reality, right, does not behave that well as the filter in the model? Yeah, some electromagnetic interference is, I mean, the filter is there to avoid electromagnetic interference, but if you look at this inductor, it's made out of lots of wires, and there will be a parasitic stray capacitance between these wires. And so at high frequencies, in this upper kilohertz, 100 kilohertz, megahertz range, right, it's very challenging and complicated for the current to go all along the windings and create a magnetic field in the core. It's much easier for the current to hop from one winding to the next over the kind of small but not negligible stray capacitance between the wires. And so this is a parallel capacitance to the inductor. And so if I need to make this a little larger, I think, but if I just introduce a 1 nanofarad capacitance and if we resimulate, boom, there's this unwanted resonance peak. And just this tiny 1 nanofarad there makes that the filter then does not behave that well anymore, but shows this resonance and then has much less attenuation that you wanted before. Yeah, so this is a bit, let's say, the final message. So you have learned what is inside the filter. You have learned how you could do measurements to characterize the filter, how you can simulate it, how you can, from the simulation, get the values of this. And what are also parasitic effects that are good and bad for the behavior of the filter. And the last thing, the very last thing that we can do now is we can take a look at the data sheet of this filter. So you can just download it from Würth Elektronik, and there you can see what's really inside the filter. It's a resistor, a discharging resistor. It's a CX capacitor, and we can check the values here. The discharging resistance is really 1000 kilo ohm. The X capacitor is really a 0.1 microfarad or 100 nanofarad. The inductance here is given as much higher because it's the common mode inductance, and we have just looked at the differential mode inductance. And if you look at the second page, there's also this attenuation figure given here, and it's given the other way around. So if I try to move my my LTspice window here to the other side, and once again tile vertically, make this a little larger and rearrange this to have it as input voltage divided by output voltage, and say okay, right, then we get pretty same curve, the pretty same behavior than what is really inside the filter. Okay, so this concludes the session. Thank you very much. See you maybe next year.